Hey everybody, welcome to HPC Tech Shorts. This is a special edition. This is the Qubit Tech Shorts, which is what we're calling it today. I'm joined this week by Jordan Sullivan in Seattle. Hey Jordan.
Hello.
Jordan is the senior developer advocate in our quantum computing team in Seattle, and she's going to be talking to us today about Amazon Braket. And we're going to get into some slightly weird things here because quantum computing is something that we, in the HPC community, we're all tracking, and I suspect we're all tracking because we're thinking that one day it's going to make us obsolete. At the very least, what we're interested in the next few years is going to be where the intersection of these two very different worlds collide. So, when Jordan and I were discussing this last week, I made the observation that I think Amazon Braket is actually spooky action at a distance as a service. And so, so Jordan, I'm going to ask you to explain us just a little bit, just for a short bit. Give us a very high-level overview of what Amazon Braket is, just so everybody starts to understand where the moving parts are.
Yeah, absolutely. So Amazon Braket, yes, aka spooky action at a distance as a service.
I don't think the acronym for that is going to work out so well.
Yeah, the acronym is a little unwieldy, maybe, but the actual service is it has a few different parts. So there's the managed service side of it, which has access to multiple different quantum computers of different types. So there's like an ion trap device, and there's a couple of superconducting qubits, and there is also a couple of quantum annealers. So there's that part of it, and then we also have a few managed quantum simulators. And then there's also an open source SDK, so you can do all the development that you want to do, build quantum circuits, access quantum devices from your local developer environment. And there's also, a whole open source repo of examples of all the way from like getting started to advanced quantum algorithms. So that's Amazon Braket.
There's a lot there. There's a lot to unpack. So we counted them the other day. There's five quantum computers. I think that's probably the best way to describe it right now. There's 5 quantum computers inside Amazon Braket.
Yeah.
Are these literally giant things sitting in, big vats of liquid nitrogen in our data center somewhere? Is that literally the case?
So they are indeed giant things sitting in vats of liquid nitrogen in many cases. They're not in our data centers. So Amazon is in the process of building their own hardware, their own superconducting quantum computer. And in the meantime, we have access to all these additional quantum computers. So you have options to explore all of the available quantum hardware that's out there.
And this is, and it's a serverless concept is the way that it's actually being served up through the API. So this is what I found really bizarre, is it's serverless. So it looks just like Lambda, only it's being done with qubits in the back end, and so it's, this is just going to be weird. And I think it's going to stay weird for another decade.
In the past, the only way that you could really get access to quantum computers was if you had an academic research grant to specifically, if you're not already a quantum computing lab yourself, to collaborate with another lab for maybe some use of their quantum computer at some point. And
you had to beg, borrow, and steal, or have $50 million to go and build one yourself.
Right, exactly.
This makes sense. So it's not I don't know whether it is the weirdest thing that we've ever done as a company, but it's right up there. This is going to be like up on the top of I've been around this company for a while. There's quite a lot of weird things that we've done, but I like this. So you're going to show us how to do a Hello World quantum style. Qubit style. Yeah. Maybe it's going to be a hello goodbye world in a superposition. Anyway, I'm going to stop making quantum jokes at this point. You're going to take us through a hello world example, right?
I am, yes.
On a real machine.
Yep. Yes, on actually a couple of real machines.
Cool. Okay.
Yeah.
Show us.
This is an example that's in our open source examples repo. You can find it on GitHub. And this is running quantum circuits on QPUs. So QPUs is, our QQuantum version of CPU. It's quantum processing unit. And so we have a few different ones. For instance, there is the one from IonQ, which is an ion trap quantum computer, and that looks like this, which is really cool. And actually, all of these like little dots that you might be able to see here are individual ytterbium ions trapped in lasers. It's called an optical lattice. It's very cool. And then the superconducting qubits. It looks a little bit less exciting, but this is probably the most popular like approach to building quantum computers is superconducting qubits, and that's also what Amazon is working on. So if we jump back to our notebook, basically we are going to just step through. First of all, this is a cell that lists all of the available gates on the different devices that we have available. So because there are a lot of different ways of building quantum computers, there are certain types of gates that are supported on different types of hardware. So there are some operations that are just either very hard to do on a particular like type of QPU or just impossible to do. So this is essentially just saying, okay, here are the like natively supported gates. If you want to do anything else that's not in those lists on that particular QPU, then you'll have to like synthesize something. So this is, and when I say you have to synthesize it, what I really mean is Bracket will synthesize it for you on the back end. Right. The native circuits, you don't have to do it yourself. So this is a Bell state, which I would say arguably is the hello world of quantum computing. And this is a 2-qubit entangling circuit. So what happens first is that you put this this top qubit into superposition. This is a Hadamard gate. It puts a qubit into a superposition of 1 and 0. And then this is an entangling gate called a CNOT. And when you entangle these 2 qubits, what happens is if they're like both initially in this 0 state, what you want to see if you have successfully created entanglement is that the 2 qubits always have the same value when you measure them. So what you should see if you measure it, like say 50 times or 1,000 times, however many, on average you should have both qubits in the same state, both 0 or both 1. So we're going to go ahead and run this. And to define a circuit, it's really straightforward. You just say circuit, do the gate that's in the picture, then the second gate that's in the picture, and then there's just like a little ASCII representation there. For this initial example, we're going to show the circuit running on a local simulator. So this is just running on my local machine in my notebook. And so the reason we're going to start with this is so that we can see the ideal case where there's no noise involved. In actual quantum computers, we're going to see that there is, in fact, noise on the state, so it's not perfectly always 0, 0, and 1, 1. But in this case, we can just run our local simulator, and it finishes super quickly, even with like 1,000 shots. That's just repetitions of the experiment. So yeah, as we can see, you get basically 50-50 the 0, 0 state and the 1, 1 state, which is exactly what you want to see. So then this is the point where we pull in our other QPUs. So we are going to start.
The real QPUs.
Yes, the real QPUs. So we're going to start with Rigetti, which again is this one. And you might have seen pictures of like quantum computers with these like really big chandeliers. Which those are what go inside of dilution refrigerators or cryostats that cool down to like cryogenic temperatures so that the materials are superconducting. It's a little bit funny because like this image has been like become sort of visually synonymous with quantum computing in a lot of cases, and it's actually not a picture of a quantum computer. It's a picture of like the equipment that you put a quantum computer on. We are going to run on this Rigetti superconducting device. So you can find these ARNs just on the Bracket AWS console. And so I've already listed that in. So we're going to do the exact same thing. We say circuit, And then we're going to do something that's a little bit different this time, where we run a certain number of shots. It's really not required in the simulator case because there's no noise on actual simulated tasks. So in theory, you could really just run it once with the simulator and you would kind of have you would have good enough data. But in this case, because there's noise, we have to repeat the experiment. So we will run this and we can see that the task was created, and we can also double check on the tasks in the Bracket console that our task has been queued at least. Oh, it may actually have already been completed. So we can see completed. Yeah, and there we go. Yeah. So really quick, we've created entanglement. The measurement results, just like we did for the simulated case, and what we see is that it's close to 50-50, 0, and 1, 1. But we also have some noise. We have some measurements where you've gotten the results 0, 1 and 1, 0, which means that the qubits are not perfectly correlated with each other, which is what you would expect if you had perfect entanglement.
So the fact that we've got noise, is that the qubits decohering? Is that the right way to be looking at this?
Yeah, exactly. So decoherence is one of the dominant types of errors that you get in quantum circuits, and what that means is that superposition is also called coherence, and so decoherence just means that you've lost the superposition, so it's collapsed into a 0 state or a 1 state. So if we go back to the circuit that we were trying to run, it's essentially if instead of this superposition gate actually succeeding in creating an equal superposition of 0 and 1, what might happen, here or here, is that after the gate was run, then this first qubit just collapses back into just 0 or just 1. And then this entangling gate won't do anything because the value that it's acting on is the qubit is now classical. So it doesn't have the superposition property from which you can create entanglement. So then we can do exactly the same thing with the IonQ device, and we can see what the status of that is. And that one is created. And now it says it's queued. And again, we can confirm that if we go to our Northern Virginia.
Back to Virginia. There's a song about that.
Might be a song like that, yeah. Like West Virginia,
yeah. I wonder if we should have a North Virginia song.
Yes.
Some country stars. Okay, so it's queued for the IonQ device.
And so IonQ, they tend to batch their jobs. So when you submit something, it won't necessarily be completed immediately, even if the device is online, because they tend to run them in batches. But we can see that it's been queued, and we've sent it off to this lovely chip in Maryland.
Awesome.
And eventually we'll get the result back.
And Oxford Quantum Circuits, is this literally up the road from me?
It is literally up the road from you, yes.
Woo!
Yeah, so we very recently launched this Oxford Quantum Circuits device called Lucy, and it's an 8-qubit superconducting device, so it's the same type of quantum computer as Rigetti.
Okay, so, this is cool. So we're gonna queue up the same thing and same circuit.
Yep. And then we can go back here and choose Europe, London, EU West 2. And
this is so cool.
From there, we can see.
Have a look at Lucy.
We can see
it's queued.
That this is queued on Lucy. And so,
also, if anybody wants to find out more, they can go, of course, to the Bracket page on our website and find out all about Amazon Bracket. Under the Getting Started tab on that page, there are some videos, and you may actually find this second video here in particular.
Yeah, exactly. So this is a pretty neat talk where we kind of talk about our vision for the future of building our own quantum computer.
The Quantum SDK, the Bracket SDK. It's Pythonic SDK, right?
That's right. Yeah.
Which is what enables you to run everything inside a notebook and for it to just look like a normal computer.
Yep.
Weird.
Exactly.
Weird. This is never going to stop being weird, I think. And if there's any other questions, if you're watching at home and you've got other ideas that you want to see us cover in the future, if you want to see us do a deeper dive on one of these areas on quantum computing, find us on Twitter. Our DMs are open. We'd love to hear from you. In the meantime, Jordan, thank you for coming today and doing this for us. That has spun my head around, and it was a really cool. That was a really cool demo.
Thank you. Thank you so much for having me.